Welcome to this video on Thevenin's theorem, brought to you by members of Tau Beta Pi. Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source V Thevenin in series with a resistor R Thevenin, where V Thevenin is the open circuit voltage at the terminals and R Thevenin is the input or equivalent resistance at the terminals when the independent sources are turned off. So let's take a look at it and see what that means exactly. So whenever we have a circuit, we can simplify it, if it's a linear circuit, into a Thevenin equivalent circuit. And that's kind of like this idea here where we just have this box, where we simplify it and we don't really care what's in the box. We just know that the characteristics of the box have a Thevenin voltage and an input impedance called R Thevenin. And so what that means basically is that if you were to hook up a multimeter to the leads A and B, you would have that voltage at the two terminals. Or similarly, if you were to read the two terminals from A to B looking for impedance or resistance, you would have that R Thevenin. And also, just to cover what it means by turning off independent sources, when you have a circuit with a voltage source, the voltage source in the circuit is turned off by shorting it to ground, so with just a wire. And if we have a independent current source, that current source is turned off by making it a open. And so that's what we'll do when we do our circuit analysis. So here's an example of a circuit that we can analyze and convert it into a Thevenin equivalent circuit. So first we have a voltage source of 50 volts connected in series with a 5 ohm resistor and a 20 ohm resistor. And this 20 ohm resistor is in parallel with our output terminals A and B. So theoretically we could have like a load resistor attached. I'll call it RL for our load. And the first part of the analysis, when we're determining the circuit for Thevenin equivalent, is to disconnect that load resistor and leave the AB terminals open. So once we have that open terminal, A to B, we can determine what the open circuit voltage would be. So let's do that. In order to find that, we'll use our voltage divider equation. So we have 50 volts times 20 ohms over the 20 ohms plus 5 ohms. So this is going to be our voltage divider, and so we know that across the 20 ohm resistor we have 0.8 times our V source, which is going to be 40 volts. So this means that across AB we have 40 volts being dropped. Also meaning that across the 5 ohm resistor there's a 10 volt drop. So the sum of those from KVL we know is 50 volts. This tells us that the voltage of the open circuit from A to B is equal to 40 volts. This is going to be our V Thevenin. Now let's look at our R Thevenin. This is going to be looking into A and B. What would be the input impedance? So just to quickly draw that, we would short that voltage source, kind of like just taking it out with a short. And then we have our 5 ohm resistor still, our 20 ohm resistor, and our AB terminals. So this looks like, to AB looking in, that we have 20 ohms in parallel with 5 ohms. So our input impedance there is going to be 4 ohms, because we have 5 ohms times 20 ohms divided by 25 ohms. It's going to be 100 over 25. It's going to be 4 ohms. So now we know that our V Thevenin is equal to 40 volts and our R Thevenin is equal to 4 ohms. So now we can convert our more complex circuit into a simplified circuit where our Thevenin voltage source, Vthevenin, of 40 volts is in series with a resistance, Rthevenin, with a value of 4 ohms. And this is open from A to B. So now, whenever we're analyzing a circuit and attaching a load to our terminals, we can simply do a voltage divider to determine the characteristics of our load. And that's essentially all that we need to do in order to do a Thevenin voltage. So here is another example, a little bit more complex, and I'll give you a second to pause the video if you'd like to try to work through it on your own. And then I'll go ahead here and just show you my work that I did. So the first thing I did was superposition, finding the terminal or the node voltage at A from the voltage source perspective. Then I did the superposition of the independent current source, and I found the current from A to B if there was a current going through that 4 ohm resistor. And then that current going through that 4 ohms is about 3 volts, or it is 3 volts. And so the sum of our voltage at terminal A is going to be the 3 volts and the 3 volts. So our Vthevenin is now 6 volts. And then looking back into A-B terminals for the input impedance, we have that voltage source shorted and the current source open, meaning that we have 4 ohms in parallel with the 6 ohm series to 6 ohm resistor. So it looks like 4 ohms parallel to 12 ohms, and we get a Rthevenin of 3 ohms. So now we can draw the simplified version of our circuit with the 6 volt Vthevenin in series with the 3 ohm Rthevenin, and it's open to our load, whatever we choose to attach. And that is the end of the video. Thanks for watching.